Hey everyone, Professor Michael Scanlan here. So in our last video, we talked about how electricity and magnetism are related. We started off down that road and we showed that around any electric current, there exists a magnetic field, and that field is in concentric circles, a circle within a circle within a circle, so forth and so on. Today we're going to look at another scientist named Michael Faraday and how he was able to show that magnetism can affect electricity. So we saw how electricity affects magnetism. Now we're going to look at how magnetism affects electricity. Now Faraday, indeed, a lot of all these scientists we're going to talk about, including Oersted, I mean, they did so much. We're just kind of picking single things that they did. Interestingly enough, Faraday was British. At the same time, or about the same time, there was an American scientist named Joseph Henry who pretty much discovered the same thing, and they both get credit for it. Even though it is called Faraday's Law of Induction, Henry still gets credit for it, and he still gets some stuff named after him in dealing with electricity and magnetism. So, what did Faraday discover? That a changing magnetic field, can produce an electric current. What do I mean by that? Well, after Oersted, in fact, Faraday talked with Oersted about his discovery. After Oersted figured out how magnetic fields come from electric currents, Faraday set about eventually, not immediately, but eventually experimenting with how magnetic fields could affect electric currents. So I have here a magnet. Let me hold it right side up so you can see. So I've got a north side and a south side. Okay, the north side is red, the south side is blue. This magnet is what we would call a permanent magnet, okay? It's not really going to change its intensity appreciably over time. Now, it will change, but not anything that we're going to need to worry about, okay? So this is a permanent magnet. It's not like an electromagnet where I can alter the current and then that in turn is going to alter the magnetic properties. This has a magnetic field around it. And that magnetic field doesn't do anything fantastic just sitting there, right? I also happen to have, this lying around, a coil of wire, okay? Now this is copper, and it's insulated, and it's got a hole through the center of it. Okay, so this is just copper wire wrapped around a plastic tube, and it's got some terminals for me to be able to connect either electricity to it, or in the case that we're going to do today, connect a meter to it. Not like a meter distance, an electric meter. Okay, so what Faraday discovered, and Joseph Henry, was that if I take this magnet and I put it in that coil, absolutely nothing whatsoever happens. Except for at the very beginning where I'm inserting the magnet into the coil. What does that do? That causes this magnetic field, see there's just Earth's field in here, nothing else. Here's an extra magnetic field. As I put it into the coil, there's a change in the magnetic field inside this coil, right? There wasn't this one's field, and now there is this one's field. That change produces an electric voltage, an electric current, okay? Now, it's not doing anything now because I actually don't have this connected. You have to have it closed, right? A wire isn't going to work if it's broken, and this is a break. So nothing's happening in here really right now. Anyway, now, if I just let the magnet sit there, well, its magnetic field isn't changing, is it? Nope. So would I get, or would I expect to get an electric current in this coil? The magnet just sitting there? Nope, not at all. So let's take a look at an old school demonstration and then a more modern replication of this. This is a galvanometer. This is an old galvanometer. This is a demonstration size. They don't make these anymore. It's really a shame when it comes to science education because our demonstrations, the scale of them are actually getting smaller, even though our classes are staying kind of big. So we have to be creative with how we do demonstrations in classes so all of our students can see. I love the old stuff though, because it was usually pretty big, and a full classroom, a large classroom, could see this very easily. We've done some work on it to try to keep this thing functioning. So a galvanometer is just something that's going to help me read voltage or current or something else, okay? I have it set up so that it's going to help me read some voltages. Now, the galvanometer itself works off of this magnetism affecting electricity thing and this electricity affecting magnetism thing, okay? So I'll explain that in just a little bit. Right now, I've got my coil that we saw in a couple of minutes ago in the last little clip. And I've got my magnet here. And the coil is connected to the galvanometer, and that's it, right? There's no power supply here. There's nothing else. So I'm going to take my magnet, and I want you to watch the needle of the galvanometer as I take my magnet and I just put it, and I'm holding it, into the coil. Now, I'm holding it. Is the needle doing anything? No, it's not. Did you notice it do something when I put it in, though? I hope so. We're going to rapidly pull the magnet out of the coil. Watch the needle. So if the magnetic field changes slowly versus changing quickly, I get a different effect. And if the magnetic field doesn't change at all, if it's just sitting in there, well, that's not doing anything either. Now, if I shake this, that's going to cause the field to change. And the needle wiggles just a little bit. But it's most obvious whenever I am rapidly changing the field through this coil. Now, if I had two magnets, the effect would be a little bit bigger. If I could move this really fast, the effect would be more pronounced. If I could just take it and just throw it through here, I would have a more pronounced motion. This is what Michael Faraday discovered. It's called Faraday's Law of Electromagnetic Induction. I think in science, the more syllables your theory has, the more credible it is. I don't know. So Faraday's Law of Electromagnetic Induction. I am using a magnet to induce an electric current, and that's what that means. Now, where does the part come in about, Oersted, where here I have magnetism affecting electricity. What about the electricity affecting magnetism bit that Oersted found? If we look in here, okay, there's some coils of wire. Now, these coils are connected to the myriad posts here. The gist of it is that as a current, an electric current runs through the wire, that wire, you can't see it, it's got a magnet, I could, and an electromagnetic video, I couldn't think of the word magnet. It's sitting in a magnet, okay, and so it's in a magnetic field. As the current runs through that wire, the magnetic field exerts a force on that current. We'll see that in a little bit, so hang on just a second. So the current running through this wire produces a magnetic field, and that magnetic field interacts with the magnetic field of the magnet itself. So more current means a stronger field from that current, and what's going to happen is more current is going to cause the thing to exert more force one way or the other. Now we're going to, as I said, look specifically at how magnetism affects current in a little bit of a different way. Not in this video. But for right now, think about it in terms of these two magnetic fields fighting each other. And the stronger one from the wire, or the stronger the one from the wire is, the more of a turning I'm going to get. So the meter itself, the measurement itself, the measuring device itself, depends on both Oersted and Faraday's work. I've got one more thing to show you. As promised, a more modern demonstration of Faraday's law. So here I have a device that's going to, when I push the lever down, it's going to run a current through this coil, okay? That current is an alternating current. In other words, the current switches direction back and forth, back and forth, back and forth, Okay, that's important. The current has a magnetic field around it, as we saw from Oersted's work. And we also saw, if the current changes direction, what does the magnetic field do? It too changes direction. So if the current in this coil is changing direction back and forth, back and forth, back and forth, then the magnetic field of that current must also be changing direction back and forth, back and forth, back and forth. So what does this thing essentially do? It creates a changing magnetic field in this area around this rod. Okay. Now this rod, I can remove it. It's just a collection of iron rods, and the iron is just there to help amplify the field. Okay. This is called a core. I have here a light bulb, and the light bulb is connected to a coil of wire here. Okay. And that's it. So according to Faraday's law, this changing magnetic field, if I were to put this closed coil into this changing magnetic field, that would induce an electric current in the wire. And what would I expect to happen with the bulb? Let's see if we're right. Here we go. Is that what you guessed? I hope so. So where the field is weaker, I don't want this to overheat. Where the field is weaker, I get just a little bit of brightness. Where the field is stronger, I get a lot more brightness, a lot more current. I don't want to burn the bulb out either. And so this is basically what? This is basically a transformer. It's exactly what this is. It's exactly how transformers work. They work off the principle of electromagnetic induction. So I hope you enjoyed this latest video in our electromagnetism series in our demonstration set. Stay safe, everyone. I'll see you in the next video.